Okay, so welcome to the first tutorial of CFD, which is on the finite difference method. So we're given to solve this differential equation using the central differencing scheme, as shown here, in this bizarre formula. Yeah, and they're subjected to boundary conditions. The whole interval is over a length L, and L is given to be a unit 1. Okay, so first we actually are given an empty length L, and we're expected to solve this differential equation over L. So the problem has already done this for us. They've already discretized the grid. So they've discretized it into 5 segments, right? 1, 2, 3, 4, 5, 6. Sorry, 6 segments. So they discretize it into 6 segments. Then what they want us to do is solve the differential equation. Okay, so first let's familiarize with all the terminology in this problem. So at the very sides, the very ends of this line, we have the boundaries. So this, they're called the boundary. Okay, the boundary nodes. Then immediately beside the boundary nodes, we have the external nodes. So these are the external nodes. And so is x1. x1 is also referred to the external nodes. x5 is also an external node. Okay, now everything in between the external nodes, we call this the internal nodes because they're inside the domain, right? They're definitely inside, they're well inside the domain. They're the innermost part of they're the innermost nodes. So we call them the internal nodes. Okay, so that's the terminology. Okay, move forward. Okay, then the second part is we'll use the modified grid. So first, let's do part A. So let's call this part A, and then the second part is part B. Part B. And they're subjected to these boundary conditions. Okay, so let's start out with the differential equation. So they have given us d squared phi dx squared is equal to phi. Okay, so in CFD, what we will do is we will approximate gradients as straight line gradients. We will approximate gradients as straight line gradients. So if I give you dy dx, okay, in other words, I can just write this as dy dx, and then you'll see why later I wrote it like this. We can approximate this as y2 minus y1 over x2 minus x1, which is what they show you here. Okay, let's go back up. This formula is actually y2 minus y1 over x2 minus x1, which is a straight line gradient we're familiar like long ago. Like I learned it in sec 1. I'm not sure about you. Yeah. So instead of using the standard results of differentiation, we will use straight line gradients to solve because we know dy dx refers to the slope on a graph, right? The slope or the gradient of a graph. So instead of using standard results of differentiation, we shall use straight line gradients, which is much simpler. Okay, what do I mean by standard results? For example, if I give you differentiation of x squared, I think most of you would know this is be power bring down power minus 1, so it's 2x. If I give you x cubed, then there will be power bring down power minus 1. Or if I give you, for example, differentiation of sine, then you know this is cos. And differentiation of cos will be negative sine. Differentiation of tangent will be secant squared. All these are standard results of differentiation. And these are accurate. They're precise. They give you every point accurately. But for CFD, it's approximate. So what we would do is, on a grand scale, we're cutting up a curve. We're cutting up a curve into many bits of straight lines. Yeah, so that's why we use straight line gradients. That's all. That's all. We just use y2 minus y1 over x2 minus x1. But it's a bit more precise than just y2 minus y1 over x2 minus x1. So let me show you what I mean. So you may not understand this now, but just take my word for it. y2 minus y2 refers to uh right, the rightmost point. Sorry, not rightmost. The point that is immediate right, okay? Immediate right. y value, okay? The immediate right y value, and this will be the immediate left y value, okay? And usually in CFD, this x2 minus x1, x2 minus x1 is a x interval, right? I take x2 and I take x1, and it'll be the distance between x2 and x1, right? X2 minus x1 is the distance between x2 and x1. So that interval is usually delta x. Delta x is the size where we discretize our domain into. Okay, so discretization means chopping up, right? Actually, we're given a line L. It's just a blank line L. But then we chop it up into 6 equal size, right? 6 equal segments. So 1, 2, 3, 4, 5, 6, right? So each of this has a size of delta x. Yeah, all of this has delta x. All of this has a size of delta x. Okay, so usually x2 minus x1 is the size of the element x, which is delta x. Okay, and let me recap. Y2 is the immediate right y value. Y1 is the immediate left y value. Okay, we'll see what that means. You might not understand what it means now. Immediate right, immediate left. Okay, but let me just show you. So what we had to do is we had to create a general template for each point. So a general template for each of the nodes. So what I mean by a general template, basically, what we're going to do is we look at each node. Let's say I'm focusing on x1 right now. Let's say I'm focusing on x1. So there's a template which captures the point and its surrounding nodes. So the point x1 and its surrounding nodes, namely x2 and a. Okay, and then we're going to do the same thing at x2. So the point and its surrounding nodes, namely x1 and x3. Okay, and then if I focus on x3, the point, and then its surrounding nodes, so x2 and x4. So all of these, each thing that I'm doing is the general template for each node. And we're going to focus on that so that we can solve the differential equation at each point. Okay, so let's create the general template. So remember, we have the point. Let's label this point as P, okay? P for point. And then its surrounding nodes. So let me forgive my drawing right now. Okay, and its surrounding nodes. So the surrounding node is its left and right. So to the right, we will call this as uppercase E, and then to the left, we have uppercase W. So E stands for east, like the compass direction, and W stands for west, also like the compass direction. And why do we label this? It's because on the compass, right, north is upwards, south is downwards, then east is rightwards, and west is leftwards. Okay. Uppercase E, or I will just call big E, okay? I'll refer to uppercase W as big W. I'll refer to uppercase E as big E, okay? Big East, big West. Big East, big West. Both of them are at a distance of delta X away, right? Because they're the points to the left and right. And we've already said that we discretize it into segments of delta X. So both of them are at a distance of delta X away. Now, in between them, we have small east and small west. Okay, so small east, small west. So you see, small east is at a distance of delta x over 2, basically half a segment, and so is small west, delta x over 2, half a segment away. So this is what I mean by it points to the immediate left and to the immediate right. You see, both east and west are to the right of P, right? When I focus on P, to the right, we have east, we have big east and small east. Small east, big east, small east, big east. Both of them are to the right of P. But to the immediate right of P, we have small east, right? Because directly beside the point P, we have small east. But then big east is like two little segments away, okay? Two little segments away. So we can't say this is the immediate. This is the immediate left, okay? So let's just say, for example, I look at point E. Then to the immediate left is point P. and then to the immediate right is big E. Okay, let's say I look at point W. To the immediate left is big W. To the immediate right is point P. Okay, so that's what I mean by immediate left and immediate right. Okay, so now let's go back to the differential equation. The differential equation we have is d squared phi dx squared and phi, right? So this, I'm going to break down the second derivative as this. Okay, I'm sure you know, right? The second derivative is just the derivative of the first derivative. So basically, I'm splitting this into d squared phi dx squared. Okay? Now, we're going to approximate this derivative. How are we going to do that? We think of this whole chunk, right, as y. Remember, I wrote this formula? dy is approximately equal to y2 minus y1 over x2 minus x1. Okay, and I said before, this one is to the immediate right, this is the immediate left, and then both of these together will be delta x. Okay, just one segment. Now, why is that case? Why is that the case? So let's go back to looking at this. When we look at the general template, we are now standing at P. Okay, we're now standing at P. So we want to find d squared phi dx squared at the point P. Okay, and then remember we say that we have this. Okay, we have this. So we're gonna use how we're gonna apply this formula to find the second derivative. How are we gonna apply this formula to find the second derivative? So using this formula, this means d dx. Okay, so now I'm finding this whole thing. Okay, of d phi dx will be approximately equal to, okay, this thing to the immediate right. So the immediate right is east, correct? And then to the immediate left will be small west. Okay, small east, small west divided by the interval. Okay, the segment. See? So let's go back up here. So to the immediate right, it's small east. To the immediate left, it's small west. That's why I take this. See? Immediate right, immediate left, immediate right, immediate left, which is small east, small west. Okay? This is what I'm doing here. So this is how you approximate second derivatives in CFD by using this y2 minus y1 over x2 minus x1 formula. Okay, now we have to further evaluate these derivatives here. So inside this fraction, we see these derivatives. We're gonna have to continue to simplify this over. So now we want to find d phi dx at the point E. Okay, so evaluated at the point E. So we're standing here now. Now, remember, dy dx is given by immediate right, immediate left. So the y at the immediate right, the y at the immediate left, then divided by the interval. So the interval we are talking about is this. You see, notice that this is delta x, okay? This whole interval is delta x. And then to the immediate right will be phi e. To the immediate left will be phi p. So therefore, this will be equal to right minus left divided by the segment. So this is how we approximate d phi dx at the point small e. Now we have to do the same thing for small west. So now we're standing at the small west. We have to find d phi dx at west. So again, immediate right minus immediate left divided by the segment, the entire segment. So to the immediate right, we have phi p. To the immediate left, we have phi w. Okay, big W. So that means, according to the formula, it would be to the right, to the left, divided by the entire segment. Okay, so now what we're going to do is we're going to take these results, and then we're going to substitute it into here. Okay, so that means this will be okay, so immediate right minus immediate left divided by the interval minus immediate right. So this is P minus W divided by delta X over delta X. Okay, now we're gonna have to simplify this fraction because it's a bit too ugly, so to speak. So I want to get the denominators. I want to get rid of the denominators at the top. So what I'll do is multiply the top and bottom by delta X. This also multiply by delta X. So at the top, if I expand this times this, the delta X will cancel, correct? And then this times this whole term, the delta X will cancel also. So basically the delta X at the top will cancel. This cancels with this. Okay. So what we're left is at the top. So now let's check this carefully, and we'll do this mentally. So minus 5p, minus 5p. So minus 1 is minus 2. Okay. Minus 2 5p. And then don't forget that this negative will distribute both to phi p and phi w. So let's look at phi w. Since phi p is already gone, okay, so minus should give me positive, right? It should give me positive. So that's why this will be positive phi w. And then delta x times delta x is delta x squared. Okay, so this is how we obtain an approximation for d squared phi dx squared. So let me recap what we're doing. So we start off with the differential equation, right? At the left hand side, we have d squared phi dx squared. We split it up into like this. Then we have to use this formula. So first we will approximate the double derivative as a difference in the first derivatives. So you see, this is a difference in the first derivatives divided by the difference in the x. Okay, difference in the first derivatives divided by difference in the x. So immediate right minus immediate left, immediate right minus immediate left divided by the segment. Okay, and we have to further approximate these first derivatives inside here. So immediate, you see, immediate right minus immediate left divided by the segment. The immediate right minus the immediate left divided by the segment. Okay, and then we simplify this, and then we should get the left-hand side. So this is only the left-hand side. Now we will equate it to the right-hand side. So what we're going to do is we're going to take this result, and then we're going to substitute it into the left-hand side. So let's go ahead and do that. So okay, remember that we are evaluating this differential equation at the point P. Okay, we're looking at the point P right now, and then we write this differential equation at the point P. So therefore, this is not just phi, it's actually phi P. Okay, because we're standing at the point P right now. Okay, so now we just simplify this. So what do I do? I'll move this delta x to this side. So I'll actually get x squared. Okay, and then I'll put phi p together with this term. Okay, notice that I can factorize out negative phi p, negative phi p. Okay, I'll factorize out negative phi p. So negative phi p. Okay. So what is the value of delta x? In this problem, we have the line L, right? The line L is being cut up into 6 equal pieces. So 1, 2, 3, 4, 5, 6. Okay, 6 equal pieces. And this line L, we're given it as the length of 1. Right? So 6 equal pieces, that means delta x is just 1 divided by 6, right? It's 1 divided by 6. So actually, I've this thing already calculated as a list from the solution sheet. Okay, so let's have a look. Okay, on the solution sheet, we have this list, which is convenient for us. So what I'm going to do is I'm going to substitute in here. So see, we already calculated that delta x is actually 1 over 6. So this I'll substitute as 1 over 6. And then you see, we have 2 plus 1 over 6 squared. They've already evaluated this for us. See, 2 plus 1 over 6 squared. This one we already substitute as 1 over 6. 2 plus 1 over 6 squared is 73 over 36. Okay, 73 over 36. Let's just put it down. We plug it in. Okay, now this is actually the general template. Remember that we're using this general template and we're gonna copy paste, copy paste, copy paste this to each of the node. So what do I mean? So remember, we're gonna copy paste that general segment over the grid. So let's say we have the grid here. So let me get a picture of this grid. Okay, so that general template, let's first paste it at the point 1. So now at point 1, P is x1, then big east is x2, big west will be A. Okay, so that means if I use this equation here, then I have to substitute. Okay, I have to substitute. Big east will be x2, right? So that means I replace phi east with phi 2. And then here, I'll replace. Okay, let me just use this equation at the top. So you see, the east pertains to point 2. So that means I'll replace this with point 2. Then point P is now point 1. So this I'll replace with phi 1. And then point W, big west, is now phi A. So this I'll replace with phi A. So that's what I'm doing. I'm going to do this for each of the segments. Okay, so each of the segments, and that's what I'm going to do. This divided by 36, phi 1, then plus phi A. Phi A. So they already told us, right? Phi A is the boundary condition. And they told us the boundary condition is, yeah, phi A is equal to 1. Phi A is equal to 1. Still 0. And then I'm going to rearrange this equation to give me negative 73 over 36 phi 1 plus phi 2. And let's check if this is the solution. Yeah, indeed, it is the solution. See? This. So what you're supposed to do is, you're going to do this for every point. Now, let's check if I can get point 2. Okay? Let's check if I can get point 2. So let's again reuse this thing we've derived here. So now okay, remember? Okay, let me just put this here first. Just put it here. So at first we're looking at point 1, right? So this is the west, this is the east. Now we're gonna use this template, but we're gonna move it over, we're gonna shift it over into point 2. So point P will now be point 2. And then we write that equation. And then after that, when we're done, we move it on to point 3. And then that will make another equation. And then we're gonna move on. So point P will now be point 4. And then write the equation. And then move on. Then point P will be point 5. Then we write an equation. That is what we're doing in CFD in general. Okay. So let's see if I can get the second equation. So now this is the point. So that means point P is now point 2. Then to the east is phi 3. And to the west is phi 1. Okay. So now let's see if I can get the equation. So the second equation will be phi 3 minus 73 over 36 phi 2 plus phi 1 equals to 0. And then let's just rearrange this in ascending order. So phi 1 minus 73, 36, phi 2 plus phi 3 equals to 0. So let's check if we get this in the solution. Yep, it's correct. Okay, it's correct. So you will do this for point 3, point 4, point 5, and remember to take care. Point 5 is the boundary condition. Okay, that's how this negative 1 over e arises. It's from the boundary condition. Yeah, and so that's how you solve part A. Now let's move on to part B. So part B, is a modified grid. So let's just bring down this modified grid. So again, you start off with the differential equation. So start with this equation. Now, the difference between the part A and part B is that here, part B has different external nodes. What do I mean? You see, look, the external nodes are now half a segment away from the boundary. Half a segment away from the boundary. Whereas the internal nodes are, still one full segment away, one full segment away, one full segment away. Okay, so it's gonna be different. How we're gonna do this is it's gonna be different. So the easiest thing is to do is let's look at we're gonna evaluate the differential equation at the internal nodes first. The internal nodes first. So let's take a look. So what we'll do is this one, we'll put aside that. At 2, 3, 4, we have this differential equation. We're gonna evaluate these differential equations at these internal nodes. So the general template for these internal nodes is like this. We have P, big east, big west, small east, small west. Oh yeah, just the tip. To differentiate between capital West and small west, see, notice that I put a serif. What is a serif? Some fonts, right? Some fancy fonts. They have these lines at the very end. These are called serifs. That's how I differentiate between the capital West and small west. Okay, the capital West and small west. So so this will represent this can in one situation will represent 0.2, and then we move on, then it will represent 0.3, and then we move on again, then it will represent 0.4. Okay, so these are this represents the internal nodes. So again, we will split this. Okay, so now remember we're standing at this point. So to evaluate this derivative, we take the immediate right minus the immediate left, then divided by this entire. Sorry. Not that. Sorry. I meant the immediate right, right? So immediate right, and then the immediate left, and then divided by this segment, which is delta x. Yeah. Okay. So we take this, the immediate right minus the immediate left divided by delta x equals to 5. And remember, we're doing this at p, right? So we have to replace it with 5p, okay? Because we're standing at p right now. We're standing at p. Then after that, we're looking at left, right, okay? Then again, we have to evaluate these now, okay? So what is that? So let's have a look. So it's actually just the same as before. So now let's evaluate at this. So we want to find this one, right? We want to find this evaluated at small east. So let's stand at small east, and then look, immediate right will be phi east, immediate left will be phi p, and then divided by this segment, which is delta x. Okay, so let's go ahead and do that. Immediate right, immediate left, divided by this segment. Then same with the d phi dw. I mean d phi dx evaluated at w. So let's get rid of this. I'm standing at w. Immediate right, immediate left. So this is phi p, phi w, phi p minus phi w. Then divided by the segment. Okay. Immediate right, immediate left. Sorry. It's supposed to be P, right? P, W. Okay. And then now, take a look. So, I multiply the top by delta x. I'll multiply the bottom by delta x. So remember, this can all cancel. And now we will simplify the top. So -1 minus 1 is -2. And then minus times minus will be plus. Then delta x times delta x is delta x squared. Okay, then I'm just gonna move everything and simplify them, okay? So I'll move this over, and then after that I'll simplify the equation. Then I should get this, which is exactly the same thing as before. Okay, exactly the same thing. Okay, but be careful. This is a different value. Earlier it was 1 over 6, right? But then let's take a look. What is the value of delta x in this case? So look at this. This is half a segment. This is half a segment. So let me put this carefully. Okay, so this half and this half, okay, both of them together will make one whole. Okay, half a segment will give me one whole segment. So actually, let's take account. How many segments are there in this discretization? So one segment, two, three, four, five. There are actually five segments. Okay, these two are gone already because I already combined them for one whole. So there are five segments actually. So that means delta x is not 1 over 6. It's actually 1 over 5. Yeah, so it's 1 over 5. Okay, so if I sub that in, I sub this as 1 over 5. Then I evaluate this. This should give me uh 51 over 25. Wait, hold up. 5 W. Let me check. Yeah. Okay. So you see, we can now put this template over what? Points 2, 3, and 4, right? So at point 2, this will be 2. Then to the east is actually 3. Then to the west is actually 1. Right? 5, 1. Then we do the same thing. So at point 3, sorry, this is 0. To the to the east of 3 is, right? Let me just draw this out. 3, 2, 3, 4. This is the east. So this will be 4. Then this will be 2. Okay, this is the west. Okay, then for point 4, you do the same thing. So this will be what? It'll be 5 now. And then to the west will be before that, so it'll be 3. Okay, so actually the solution, what they do is they arrange it in ascending order, right? So actually for here, they'll start with 5, 1, right? So let's check. But they're actually the same. They're actually the same thing. It's just that in the solution provided, they arrange it in ascending order. So like 5, 1, 5, 2, 5, 3, and then 5, 2, 5, 3, 5, 4, and then 5, 4, sorry, 5, 3, 5, 4, 5, 5. Yeah. So let me check the solution. Yep. So you see here, they arrange it in ascending order of 5. So here, we got the solution. It's correct. Now we have to check the external nodes. The external nodes are treated differently. So what do I mean? The external nodes cannot use the general template. Why? Because the general template that we use, right? Take a look. The general template that we use, the points beside it are both at a distance of delta x away. Delta x. But then, at the external nodes, beside it, there is like a half segment away. See, this is half a segment away. Half a segment away. So we cannot use the general template. So we have to create a new separate template for the external node. So let's have a look. So this is the template for the external nodes. Let's think of the point 1 first. Point 1, this is phi A, this is phi 1, and this is phi 2. This is point 2, this is point A. Okay, so okay. So again, we always start out with the differential equation. So they give us this differential equation, right? But now we're going to do this at point 1. We're going to evaluate this at point 1. So instead of phi, this will be phi 1. Okay, this we split it up. And then we're going to evaluate this at point 1. So we stand at point 1. Okay, so it's better for me to draw the template first, because the template has the letters in terms of east, west, and then the point. So what do I mean? I mean like this. So here we have point P. So this is P. To the right is east. To the left is west. Sorry. This would be small west. Okay, small west. Because it's half a segment away. Then this will be small east. There is no big west. There's no big west because it's outside the boundary. Okay, so there's no big west. So we're standing over here, right? Now, immediate right, immediate left. Okay. So to the right, we have this evaluated at east, and then minus the immediate left, we have this evaluated at west, divided by the segment. Okay, so now let's find the value of this. We're gonna have to simplify that. So now I'm standing over here, right? This is the east. So to the immediate right, I have big east. To the immediate left, I have the point P. So that means this is actually phi, this phi east minus phi P divided by the segment minus. Okay, now we have to evaluate this derivative at W. So now I'll be standing at W. So this is the case where we cannot use the full segment, right? Because there's no immediate right. We have the immediate left, but then we don't have the immediate right of this point. So how are we supposed to find the derivative at W? So what we would do is we will use an approximation called the forward differencing scheme. Forward differencing scheme. Now let's see why. See, the right words in one dimension, right? The right words is forward. Forward. Left words is backwards. So backwards. Hold on, I need to get my charger first. Okay, where was I? Okay, so I'm trying to evaluate d phi dx at W. But the problem is we need to use the forward differencing scheme. So why is it called the forward differencing scheme? So let me just show you what is the forward differencing scheme. Because we do not have the immediate left in this case, we cannot use it. So as a compromise, we will evaluate the derivative over this segment. So let me just highlight. We will evaluate it over this segment. See, let's say normally, for example, at E, right? If you want to find d phi dx at E, we can use the central differencing scheme because we stand at this center and then we evaluate the difference over the entire dx. But then now at W, we cannot do that because we don't have the left side value, right? We don't have the left side value. So what we would do is we'll go forward. Sorry, I don't know why I turned a hexagon. We'll go forward to look at this value. So we will evaluate the derivative over this segment. So instead of delta x, it will be now delta x over 2. So if we look at this segment, we have to the right, to the immediate right, which is phi p, then we have no choice, we have no immediate left. So we have to just use the point that we are standing on. So we just use the point that we are standing on, which is minus phi w divided by the segment or the size of the segment. So this is delta x over 2. Okay, so we use the immediate right, the point we're standing on, and then divided by the segment, which is delta x over 2 now. Okay, it's not just delta x, it's delta x over 2. Okay, so this is the value of d phi dx evaluated at w. So this is phi, let me check, p, right? P. Okay, so now how are we going to process this? So, see, notice that this is not delta x, it's delta x over 2. So we need to get rid of that annoying 2. So how do we do that? We multiply the top and bottom of this fraction by 2. So this 2 and this 2 can cancel, right? And then this 2, you distribute it to here and to here. So what we'll get is, uh, 2 minus 2w. Right? This is small w, okay? This is small w, it's not big W. Okay? Then we want to get rid of this delta x, so we multiply top and bottom by delta x. So this cancels with this, cancels with this. Then now we evaluate the top. So this is minus 1, minus 2 is minus 3, okay? Minus 1, minus 2 is minus 3. And then don't forget, minus and minus will give me plus. Okay, so at the top we have this, minus 3 by p plus 2 by small w. Then divided by delta x squared. Okay? So now let's substitute in the values. Remember that we are doing this template only at phi 1, right? So phi p is actually phi 1. Then this phi w, we're given the boundary condition, correct? Phi w is the boundary. Remember, this is the boundary point. So actually phi w is actually phi a. And phi a, they told us, is 1, correct? That's the boundary condition that they give to us. Yes, okay? Phi a is actually 1. So that means I can substitute this as 1. Okay? Then, yeah, so this thing, remember, is 1 over 5. So it's actually 1 over 5 squared. Okay, so I'll move this over. So I'll move this over. So remember, don't forget, we need to square this, so it becomes 1 over 25 by 1. Then this is by east. East is to the east of point 1. Yeah, the point east of point 1 is point 2. So this is actually phi 2 minus 3 phi 1 plus 2. Yeah. Now I'll bring this to this side. So minus 3 minus 1 over 25. Minus 3 minus 1 over 25. It will be... So you just rearrange this. Let me see the rearrangement. If you rearrange this whole thing, you should get 76 over 25 by 1 plus by 2 is equal to negative 2. Yeah, you rearrange this whole thing, you should get this. Let's check if this is the answer. And yeah, correct. Correct. Okay, so now finally, let's do 0.5. 0.5. So again, let's draw up the 0.5. So this is actually the boundary. So this is B. Then half a segment away, we have 5. Then a full segment away, we have 4. Okay, so let's draw the general template. The general template like this. This is point P. This is the small east. There's no small, there's no big east, okay? There's no big east. Then you have big west. Then small west. Okay? So start out with the differential equation that they gave us. They gave us this differential equation. Okay, remember we're gonna evaluate this whole differential equation at point P, which is 5. And split this up. Okay, so now we're doing this, we're evaluating this at 5, right? We're evaluating this at 0.5. So what we're gonna do is we're gonna stand at 5, then we look. Wait, let me think. Yeah, we look at the immediate right. So to the immediate right we have, let's look at over here. To the immediate right we have east, to the immediate right we have west. Okay, so this will actually be phi ex at east minus the phi ex at small west over the interval. Then this one, so we're gonna stand at east now. Now you see, if we stand at east, let me just increase this marker size. So if we stand at east, oh, this is too big. So if we stand at east, there is no immediate right. So we're gonna have to use E. We're gonna have to use the small east as the immediate right because we have no right. So our only choice is to use the point itself as the right point. Then to the left, we do have a point. Okay, so d phi dx at the point E, we use the point itself because we don't have any right. We're going to use the point itself minus to the immediate left, which is P. Yeah. Okay, so this, we're going to substitute it into our differential equation. So this. Then this will just be like normal. Okay, so you stand at west, immediate right is P, immediate left is big west. So okay, so to simplify this, top and bottom of the x, this will cancel. Then we evaluate the top. So you do this carefully. I'm gonna go through this quickly. Wait. Be careful, be careful. I made a mistake. I made a mistake. I made a mistake. Remember, we're doing this, the backward differencing scheme, right? This is wrong. Sorry, this is wrong. It shouldn't be delta x. It should be delta x over 2. Okay, it should be delta x over 2. Why? Because let's have a look. Okay, let's have a look. Remember? When I evaluated at this point, I'm only taking the derivative over this segment. This derivative, this segment is not the full segment, it's half a segment. So I shouldn't be dividing by delta x, I should be dividing by delta x over 2. Okay, so it should be delta x over 2. This should be delta x over 2. Then let's multiply the top and bottom by 2. So this times 2 times 2. So this 2 can cancel with 2. Then I distribute it to the top. Then I can multiply the top and bottom by delta x. So this will cancel and cancel. Then you simplify the top, so this top will be what? P. Okay, you do this carefully, okay? I'm rushing through the steps because this video is taking really long. Okay, so now you replace this. So delta x, remember, is actually 1 over 5, right? So 1 over 5 squared is actually 1 over 25. I'll put it here. Then east is actually phi b, right? Phi b, they told us is 1 over e, if I'm not mistaken. Phi b is, yeah, 1 over e. This is actually 1 over e. Then this is actually the point, which is by 5, and yw to the right is by 4. Okay, so if you rearrange this, you should get 5, 4 minus 76, 5. So basically, I'm just simplifying, putting everything in the right place. You should get this, which is correct. Okay, so that's it. As long in CFD, as long as you can get these equations, you're done. What we are interested in are the equations, because the equations will help us to evaluate the points. So what do I mean? Let's say we take this set of values, right? We take this set of values. Look at what this whole thing is. This is a system of uh 5 equations with 5 unknowns. So that means we can find phi 1, phi 2, phi 3, phi 4, phi 5. We can solve. These are solvable. Solvable. So what that means is, after we solve this equation, right, we should get this number, this number, this number, this number, and this number. Okay? And then after that, what we can do is we will plot these points, plot this, plot this, plot this, plot this, plot this, over the grid that we discretized. Okay. Then after that we can get some shape, and then after that we can compare it to the actual thing. Okay, but this part is unnecessary. What we're interested is getting this. Okay, this is the most important thing that we're interested in. Whereas this is how we can kind of see the general shape of the function. So this is actually phi of x. Okay, so that's it.